Okay, so this is the 6-week exam from 2022. I'm just going to go through each of the problems and try to show you how it's done. So let's get started with number 1, which is a data movement problem. So there's a bunch of instructions, and we're just trying to figure out what happens in all of the registers in memory when each of these executes. So we start with basically just walking through each instruction and then showing what the updates are. So first we've got to move W R0. And I'm going to show this off to the side just to show the sort of in progress update, right? So move W zeros out the top 16 bits or the leftmost 16 bits. And then it sets the value in the immediate in the rightmost 16 bits. So after the first move W instruction, this is what we're going to have as our value. After the second one, move T sets the leftmost 16 bits to the value in the immediate. So this is going to be our full update to R0. We'll have BADC and then AFE1. So that should be our final value for that after those first two instructions. The move W gives us this first value, and then the move T sets the second value in the leftmost bits. So that leads us into the move T, R2, which sets ABCD. And the important thing here is we're only overwriting part of this R2 value. So ABCD is going to overwrite the leftmost bits of that. We're still going to have the FFFF there from the original value that was in R2. So that's just testing the semantics of the move T instruction. Next up, we've got a store. So R3 goes into the memory address in R1. So keep in mind, the thing in the brackets is a pointer to memory, and that's what we're looking for here. So we need to look at what R1 is. R1 is OX10000200. And so we're going to go to this place in memory, and we're going to look at, because it's an STR, we're going to be modifying those 4 bytes of memory. So it's not store half word or store byte, it's just a full store, which means 32 bits, which means 4 bytes. So we're starting from that address. We're going to change 4 bytes of memory. And so we're going to put the value from R3 in there. Keep in mind the way R3 is written, we're going to want that in little endian order. So the little n is going to go first. So 0953. We're just basically looking at each 2 digits there is a byte. So 0953. 6718 is what it's going to look like in memory. So then we're going to overwrite the bits that we found earlier with those values 0953, 67, and 18 are going to go there. So that's the store instruction is modifying that. LDRSH, so a load instruction is going to get something from memory and it's going to put it into R4. So we're going to be changing the value of R4 here. We're looking for R1 with an offset of OXC. And so R1 is still storing 1000,200. So we're going to that location in memory. And then we want to be able to basically count up 1, 2, starting from 0, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, right? That's 10, 11, 12, 13, 14, 15 in hex. So starting from the leftmost address, when we do this, we're counting up by this much each byte as we go over, right? And the leftmost one is just at that address that's listed, right? It's a 0 offset. So you can think of this as like +0, +1 as we go across the page in this memory diagram. So to get to 10000020C, since we have here, we have our base address of R1, 00200, plus OXC is our offset. That's going to give us 10000020C is our final memory address that we're looking at. So we want to find, there's the C column, and we are getting a LDRSH. That means this is a signed half word. So we're going to get 2 bytes from memory. That's the 7, 7, and 8, 8. That is in little endian order. So we're going to end up getting 8, 8, 7, 7. And then we need to do the sign extension. So we're looking at the leftmost bit of 8, which in binary is going to be 1000, right? So that means when we do the sign extension, we're going to copy a bunch of 1s ahead of this, which is going to end up being F's in hex. So we're going to end up with the final value here of OXFFFF8877 due to the sign extension. Last couple instructions here. So we have a couple pushes and then a pop. And so we want to remember what a push instruction does, which push of a value is actually a sub SP or R13 by 4, right? So we're going to subtract 4 from SP, and then we're going to store our value Rn into SP or R13. So we're basically going to decrement R13 by 4, and then we're going to store to that place in memory. So let's sort of show this as it happens. Remember that when we have a push, we're going to go largest number, largest N first, gets pushed into memory. So we're going to push R3, and that means we're going to subtract 4 from 100200. So it's going to become 100001 FC. When we subtract 4 from 200, that's what we get. So we want to find that 1 FC is going to be these 4 bytes are getting replaced. So we're going to scratch those out, and we're putting the value from R3 there. So we're going to have that same value that we had over here. We're going to basically just copy it in 0953 because that's when we stored R3 into memory. 6718. We could just push R3 into the memory here, so we're storing it there. We're going to do the same process, so we're going to subtract again. We're going to have OX100001F8. Now as our stack pointer, we're going to find that in memory. That's these 4 bytes. So we're going to scratch those out, and we're pushing R1. So we're going to end up with, again, the individual bytes of R1 stored there in memory. So 0020, or 02, sorry, 0010 are what are going to be in memory there. That's our push instruction. So we're done with the push at this point. Now we're going to do a pop. Pop is load into Rn from current stack pointer, and then add stack pointer by 4. All right, so we're loading something into the register given, so that's R5, and we're getting incrementing the stack pointer by 4 when we do that. After we do that, so R5 is going to become the value that's currently in memory there. So that's going to be the 10000200 value that we're taking from here in memory. That memory doesn't go away; it stays there until we overwrite it with another push instruction. And I should keep in mind for pop, we do smallest N first. It is the reverse of the push instruction whenever we take that value. So it's sort of this push and pop are the reverse of each other in every way, right? And then we do the add. So we're going to end up with OX100001 FC as our final value for R13. So that is it for those two. I think the pushes and pops are probably the hardest to understand what's going on just because they're doing multiple things, but hopefully that helps.